to the third in a series of debates between Professor Eric Sullivan and Professor Kelly Klein. My name is Ted Wendt. I'm going to be moderating to the best of my ability here. So in the first two debates, we talked about things like theorems, and what was the second one? Unsolved mysteries. Right. So we talked about a lot of cool mathematical things. One of the neat things about mathematics, and one of the things that really attracted me to mathematics, is this wonderful mathematical history. You can look back through history and see tremendous mathematical achievements by the Babylonians, by the Greeks, by the Egyptians, by Indian mathematicians, all sorts of wonderful things. And if you look at the way that we learn or teach mathematics throughout the curriculum, we learn about things like algebra, which has a history of thousands of years. We have geometry, which has a long, long history. Then a little bit later, we have something like calculus, which still is 300-400 years old in the making. Even statistics has its roots several hundred years ago. But of course, that means you probably ask yourself, all right, math, if you're so cool, what have you done for me lately? And tonight, we're going to answer that question. So tonight, the discussion is, what is the greatest mathematical achievement of the last century? So in our lifetimes, what has math done for us? To get century. Huh? I'm saying that some of us. Fall in that color. Yes. So, to get started, we will do a coin toss. You lost the last day, right?
I don't remember.
I think you get the chance to call it in the air.
Okay.
Great. Call it. Heads. Heads it is.
I choose to go first.
All right. Mr. Clark, you go first. Pull it up.
All right, so we're here to debate the greatest mathematical achievement of the last century, and I think it's pretty clear that that achievement, which has impacts all over our real-world lives and the theoretical, all sorts of wonderful things, is the achievement of public key cryptography. So we need to talk about this. So here's the scenario. I want to buy a book from Amazon, or order a plane ticket from Expedia, or buy something online in some way. What that means is I get to send my credit card number over the internet so that the people there can check that my account is still valid, all that sort of thing. The internet, by design, is not secure. It's very flexible, it's very reliable, it does really well, but it's deliberately designed in such a way that it cannot be made secure, which means there could be bad guys along the way recording copies of things and stealing my credit card numbers and then booking their own trips to Tahiti or something like that. So what that means is I got to take my numbers and I got to put them into some sort of code so the bad guys can't do that. But here's the problem. Amazon and Expedia and all these things, they've got potential customers all over the world. So what that means is they have to tell everybody in the world, anybody who goes to their website, how to encode their stuff. But that would include, the bad guys, potential thieves, and all that sort of thing. So if we're going to tell everybody out there how to encode things, and the thieves know that too, couldn't they just use that to undo the code and figure out what my credit card number is, and then tap me out and make my account go dry? What I need is something amazing, something strange, something that seems like it shouldn't even be possible. I need a sort of code which I can tell everyone in the world how to put it into code, but even if you know how to put it into code, you cannot decode it. I need what is called public key cryptography. Public key meaning I tell everybody how you put it into code, and but I don't tell anybody how to decode it, or Amazon doesn't, so only they can do that. That seems like that shouldn't even be possible. That shouldn't be a thing. I mean, isn't that how codes work? The simplest sort of code is what we would call like a substitution cipher. And those have been known since ancient times. Julius Caesar used these in order to communicate with his generals. And basically what you do is for every letter gets mapped to one other letter. For instance, if I want to say hello, I could translate H is mapped to U, and E is to R, and L is to Y, and all this sort of thing. And that's the simplest sort of cipher, the very most basic sort of code. That's not going to help me keep my credit card numbers safe when I transmit that over the internet because, well, if you know how to encode it, you know how to decode it. Basically, up until the 1970s, every method of encoding anything was the sort of thing where if you knew how to uncode it, you could decode it. And so I need something different. I need something amazing. I need a code system which will, and I can tell anybody how to do it, but only I can undo it. And this was developed in 1977. I think this has got to be the most amazing, incredible, powerful, useful, surprising, astonishing mathematical discovery of the last century. Here are the three people who did it. They're at MIT: Ron Rivest, Adi Shamir, Leonard Edelman. So we call it the RSA after their last names. It's what we call the system, their algorithm for doing this. They came up, they published a paper with a real-world practical system that really can be used in an everyday situation so that Amazon can tell everybody how to put things into code, but only they can take it out of code so my credit card number stays secure while I order that book. And the key idea behind this, the secret sauce, the thing that makes this absolutely wonderful thing happen, is our prime numbers. Now, prime numbers, okay, so we got all these, so we got all that, the whole positive numbers here. All those numbers, I can classify them into composite numbers and prime numbers. A composite number is a number where you can get it by multiplying two others together. Like, for instance, 10 is a composite number because 2 times 5 is 10. On the other hand, 11 is a prime number. There are no two other whole positive numbers you can multiply together to get 11. Other than 1 in itself. So 11 is a prime number, and so we've got it marked out here. 11 is prime, 12 is a composite, 13 is prime, 14, 7 times 2, that's composite, 15, 5 times 3, composite. So I can go through and I can one by one check the numbers to see if they're prime numbers or not. And prime numbers are powerful things. They are amazing, interesting things. They have wonders and powers that are even hard to describe. They've been known since ancient times. This is 300 BC. The ancient Greek mathematician Euclid, in his great work, The Elements, wrote all sorts of interesting results about prime numbers. And one of the most surprising came from him right there. He proved that there is no limit to the number of prime numbers out there. You would think that as we get out to a certain size, everything would be a multiple of something, but no. Euclid proves there's an infinite number of prime numbers. No matter how high you go, there's always a prime number above that. There are lots and lots of unsolved mysteries about prime numbers. We're still trying to figure them out. New discoveries are being made all the time. One of my favorite ones, which has been, people have worked on this for centuries and no one has figured out, is are there an infinite number of twin primes? Certain prime numbers out there where they're only separated by 1. So like 11 and 13 are a twin prime, 17 and 19 are a twin prime, 41 and 43, 71 and 73. Well, if you can prove there's an infinite number of prime numbers out there in 300 BC, you would think by now we could know if there was an infinite number of twin primes. But no, we use computers and we keep finding more of them, but no one knows for certain whether or not. There are tons and tons of mysteries. You go onto Wikipedia about unsolved mysteries about prime numbers. There's this whole list of all these conjectures and guesses and things where people are still working to try to figure this out. So. And here's the thing that makes this whole encryption thing work. Large prime numbers are hard to find. I mean, okay, I know that 11 is a prime number, and I know that 13 is a prime number, but if I want to say a big number, like 632,513, is that a prime number? Well, let's see. It's not divisible by 2 because it's even. It's not divisible by 5 because it doesn't end in 5 or 0. But is it divisible by 7? Well, there's only one way to do that. You divide it out. You check it out. See whether 7 goes into it evenly. And then you check 11, and you check 13, and you check all the other. The only way to actually check whether I've got a prime number is to one by one go through and check all the possible prime factors of it. And for very large numbers, this can take a lot of time. So if I want a huge prime number, if I want a 10-digit prime number or a 20-digit prime number, this can take an enormous amount of time as supercomputers just go through one at a time checking. And that's what makes this happen, because it's very, very hard to do this. So the basic scenario, and the truth is I can't do more than give you just a little tiny taste of the glorious ideas behind that. If you want more of this, here at Carroll College, we every now and then teach a course in cryptography, so please come give us a semester, we'll explain it all. But let me just give you a taste. All right, so basically the idea is, suppose I find 2 enormous prime numbers, fantastically huge prime numbers. I own a great big supercomputer. I set it to work for weeks on end. I find 2, and some of the largest prime numbers exist. If I take them together and then multiply them, I'm going to get an even bigger number that I'll call n. And here's what I do. I know the 2 prime factors of n, but nobody else does. Because n is this ridiculously huge number. It's a 30-digit number or something like that. I keep the 2 prime factors of that safe. And they're my private key to the code. Now, how do we do this? What's this mathematical process for making the code? Well, First thing we got to do is we have to learn how to, we take our message and we turn it into a number, which is easy because computers do that automatically. There's a certain, in computers, there's a certain number that represents A and represents B and stuff like that. And on my credit card number, that works great. There's 16 digits, all that sort of thing. And so I can do that. And the next thing we do is we take this number and we raise it to powers. We raise it to exponents. So for instance, if my message number is m, then m to the 2m squared is m times m. And m to the 3 would be m cubed is m times m times m, and m to the 4th is I multiply it by itself 4 times. And the beauty part of this is this rather than having all the different digits of this, just, this digit maps to that one and the encoded thing, this scrambles them all up. The ultimate result is going to be some ridiculously huge number, and every single digit of that has been affected by every single digit of the initial thing. So it all gets scrambled together. It's one big piece. And then the next part of this is everybody's favorite part of mathematics. The thing when they think about their lessons of mathematics from elementary school, they remember fondly the joy they got. That's right, I'm talking about long division. So here's what we do. What we're talking about is we're going to talk about finding remainders of numbers. So if I divide something by something, like for instance, if I take the number 16 divided by 3, well, let's see. I want to find how many 3s there are in 16, and I find, well, there are 5 3s in 16, but then I have 1 left over. That's, in elementary school, we call that the remainder. As math people, well, we don't want to be just talking like elementary school students. So we give it a special name. We call it the modulus, and that sounds really cool. So when we're talking about the mathematicians, we have modulus. So like 16 modulus 3 is 1, 17 modulus 3 is 2, because, 17 divided by 3, 2 left over. 18 modulus 3 is 0, because 3 goes into 18 evenly. And so these are the ingredients of it. Raising things to powers and taking the remainders, the modulus, that's the whole bit of the algorithm. So I take my message, I raise it to some big power where I get e from my prime numbers. I divide this by n, that's my big number that has only 2 prime factors that I'm going to keep private, sort of thing like that. I find the remainder. The remainder of that is my encrypted thing. That's the message that then I transmit over the internet, and then the bad guys can get that, and anybody else can look at that, and they can't make head or tail of that because only I know how to decrypt it. So I've come at brackets, I'm Amazon, and people send their stuff in, and I take that remainder, that modulus, and then I raise that to another power, which again is based on my prime numbers. I again divide it by n, my huge number, and then when all this happens, the remainder I'll get, the modulus I'll get, is my original message. Now, that's 30 seconds. I mean, that's about how it goes. But the basic scenario is Amazon, their computers tell, when I get onto my browser and I'm buying a book, or I'm on Expedia or eBay or any of these sorts of things, they'll tell everybody what values of n and e to use, what exponent to use, and what to divide it by to come up with your remainder, your modulus. But nobody can figure out what my exponent is without knowing those 2 prime numbers. Now, theoretically, if they had a supercomputer too, then they might be able to figure it out. But I'm Amazon, and I've got bigger supercomputers than they do. So, that's how it works. And so the larger my number is, the more work this will take. And so there's kind of an arms race in this, whereas as computers get faster and faster, then they have to have bigger and bigger ones. But that's how it works. So here's the question. Why does this work? How does this work? How could that be? I mean, this is, how is this process? So you raise this number to a power, you divide by this, you take the remainder, and then if that remainder is taken to another power and divided by that, the remainder of that one's going to be the original one. I wish I could go into all of that, but at this point, all I can really say, this is deep magic. This is awesome. This is the deep magic from before the dawn of time. This is the stuff that is so awesome, so fantastic, so gloriously wonderful, that you can't even believe it's true. And that's why it took this is why it was only discovered in 1977. And the essential idea, it rests on these unique properties of prime numbers. Prime numbers are the atoms of which the other numbers are made, and so they have these very powerful properties. And the discovery of how to use this in a practical way, I mean, that's amazing. This wasn't just an idea, but a full-blown algorithm that is now used 1 million times a day by all sorts of computers going back and forth. And this is a glorious thing. Without this, you couldn't have Amazon, and you couldn't have Expedia, and you can have eBay, and you can't have all these other websites where we can do commerce. We need to be able to send things securely back and forth. All of this rests on this idea that I can send information, I can send my credit card numbers, and I can be secure in that. Without this, none of this works. Last year, e-commerce was $2 trillion. And that all rested upon this idea of public key cryptography. All these, Target, Netflix, you got a Netflix account, eBay, TripAdvisor, all these sorts of things. They require this system to go back and forth, to be able to accept payment and all that sort of thing. Millions of jobs around the world rest upon the ability for us to use the internet to do commerce and interact with each other in this way. I don't want to be totally mercenary about this. Last year, $24 billion was donated to charity through the internet. My very favorite website is kiva.org. They have a total of $941 million has been, you can go on there and you can put in your money and then you can loan it to people in third world countries and things, and you can loan it to this farmer in Africa or this person who runs a store in Guatemala. It's fascinating. You get to learn about these people, make connections with these people. None of this would be possible if I could not securely do these transitions over the internet. And on another level, this is about me being able to communicate with other people in a secure way. So cryptography in general, this isn't just about me buying a book on Amazon. This is about our fundamental right to privacy, which is defended by this beautiful, awesome, lovely bit of mathematics. And there's a lot of people out there who would like to invade our privacy. The criminals, big corporations, governments, all sorts of things would like to know everything, the last thing about it. And this beautiful bit of mathematics stands to protect us and allow me to protect my privacy. And so that's amazing. That's not just some theoretical result. This is a practical, everyday sort of thing that we all use all the time. So here's my summary. Why is it the public key cryptography is the greatest mathematical discovery of the last century? First of all, the theory behind it is beautiful. It's all about the strange and mysterious world of prime numbers and the amazing power they have. That's just glorious stuff. The publication of this, well, that wasn't the end of it in 1977. Then other people can I come up with other systems of public key cryptography? This is a whole field of research. Different ways of things. This was a whole new avenue for exploration. Now many, many different public key cryptography systems have been published. Different people are researching this, making new discoveries, advancing things in a whole field of research. And there it is. And this is not only beautiful and interesting and intricate and glorious, but it's so powerful that now trillions of dollars of commerce, millions of people around the world have their jobs resting upon this mathematical idea, which was invented in 1977. And it protects our right to privacy, which is an amazingly powerful, what a gift to have something so useful, so helpful, that's just a fantastic thing. So that's why I have to say that public key cryptography has got to be the greatest mathematical discovery of the last century. Thank you.
I think everyone here would agree that is most actually one of the top two. All right. So our next speaker, Professor Eric Sullivan, is going to give his opinion on what he believes is the greatest mathematical achievement of the last 100 years.
Well, thank you, Ted. So, there's something interesting that happened here in the last 15 minutes. Dr. Klein wants you to believe that the barbarians are standing at the gate. They are pounding at the door. And the mathematicians hold the key to keeping them back. I got to admit, to some extent he's right. If that's the only thing you're interested in, if the only thing you're ever interested in is secure commerce, which is arguably quite important, I agree, mathematicians are holding the barbarians back. It's an important discovery. I'm going to talk about something far more beautiful, and far more far-reaching, and much less magical. I'm sorry, what I'm going to talk about is not just voodoo magic of prime numbers. It is something that's embedded deeply in what we understand about the world. It's actually, the name is Fractal Geometry. So let's start off with maybe kind of a weird question. How long is the shoreline of Great Britain? True, yes, long. It is long. But the weird thing is it actually depends on your measuring stick. So if we use a measuring stick that's, say, 100 kilometers long, now clearly we're going to miss some of the little dips and dives there. We're going to miss some of the bays. We're going to miss the rocky outcroppings. If I use a 100-kilometer long measuring stick, what do I get, 2,800 kilometers? Yeah, okay, it's probably close, but it's not really good enough. So let's make our measuring stick a bit better. Let's take maybe 50 kilometers. Well, now I get a couple more of the features around the outside of the Isle of Great Britain here. So now I've got 3,400 kilometers. I went up by 600 kilometers just by having my measuring stick. Well, what if we take the point of view of the human being who wants to walk around in the sand with their toes in the sand and actually walk around this island? Well, they've got a much shorter measuring stick, maybe a stride of about 2 or 3 feet. They're going to get a longer distance. What about the ant's point of view? Now, these little buggers here, they've got a long ways to walk. I mean, you think about it, their measuring stick is really, really tiny. They've got a long ways to go, but they've also got to go over every single rock and over every single sand dune, stuff that we just stride right over. Well, they've got a much longer distance. This is actually behind the scenes in this mathematics called fractal geometry. So, here we go. I'm going to hit you with the definition. What is a fractal? A fractal is a mathematical set that has a repeating pattern at every scale. And they were first kind of written about by this gentleman over here, Benoit Mandelbrot. Now, Benoit Mandelbrot, he actually passed away in 2010, and this is a picture of him giving his TED Talk in 2010. He was a brilliant mathematician. Just like Dr. Klein's work, he actually published most of his work in the mid-1970s. A year very dear to my heart. 1975, the year I was born, he published his fundamental paper on fractal geometry, and he is actually now very famous for this fractal over here. This fractal is actually called the Mandelbrot Set. So let's dig in. If we say this thing has repeating patterns at every scale, that means I should be able to zoom in somewhere on the picture and see the same picture again. So if I look at this little bulb over here, oh wait, there it is again. Oh wait, there it is again. There it is again. And again. And if we zoom in, that little bulb rears its ugly head over and over and over and over again. That thing's everywhere. And if I zoom in some more, it may be hard to see here, but that little black dot right there is an entire Mandelbrot set in and of itself. The whole thing's hiding inside the whole thing. Wait, that's weird. So I can zoom in as much as I want and I find the same picture over and over and over again? That's actually pretty cool. Now, it turns out that this beautiful Mandelbrot set is built off of really simple mathematics. It's really just take a function, do something very simple to it, and then repeat over and over and over again. Now, so I'm going to start with something a little bit simpler other than the Mandelbrot set. We're going to start with what's called the co-snowflake. All right, so this snowflake, we take a line segment, right, so just across the bottom there, some line segment, take the middle third, pull it out, replace it with 2 pieces that are exactly the same size as what I pulled out. Now obviously that's got to buckle up in between. So I make this little triangle here, and I'll do it again. And I'll do it again. And I'll do it again. And if you do this over and over and over again, you get this infinite roughness on this picture. This is a really simple rule. Anybody with a ruler and a pencil and a lot of time can do this. This is really, really simple. Now, if you apply this to something a bit more kind of two-dimensional, we actually get why they call this the co-snowflake. It kind of looks like a cool snowflake. Right, so we can actually get fractals from amazingly simple rules. So let's play a little game. It's called the chaos game. We're going to do this 3 times. So the chaos game says, let's start with an equilateral triangle. Right, we got 3 sides that are all equal to each other. I've numbered them, numbered the vertices 1, 2, 3. We pick a point inside, and then we pick a vertex. So maybe like by rolling a die or something like that. So let's say we pick 2. We're going to draw a point then halfway between our point and the vertex. Fairly simple, right? Pick a point, randomly get a vertex, go halfway between, draw a new point, and repeat. So my question to you is, if we do this over and over and over and over again, will we just fill up the entire triangle with points? Will we build a fractal, or is it that you just simply have no idea what we're going to build? So I actually want to show of hands here. So how many people think that we're actually going to fill in the whole triangle? We got like 7 people. Okay, we're going to build a fractal. Far more people. How many people are bold enough to say, I have absolutely no idea? Excellent. Good. And I noticed that some of you voted twice. So let's look. Yeah, you got to hedge your bets, right? So let's watch. All right, so I've got a video here. I've YouTubed this thing. So my starting point is that little dude up there. And we're just going to let this run. We've got some code that's just doing this same process over. Wait a minute. Nothing's happening in the middle. Oh wait, and that upside down triangle is also there. And is also there. And is also there. And there. And there. What the heck? I'm getting the same structure over and over and over again. So out of these really, really simple rules, it appears that I'm actually getting something that looks like a fractal here. Well, that's pretty cool. Let's try another one. All right, chaos game again, so it's basically the same rules. This time I'm going to play the game on a square. So we pick a point, we randomly pick a vertex. Let's say it's 3 this time. We draw a point halfway in between, and repeat. What do you think? How many people say we're going to fill the square? Daniel, you're the one. Okay, we got 1 that says we're going to fill the square. Create a fractal. Because now I've led you to believe that that's what's going to happen. How many people still are claiming they have no idea? Right, thank you. And again, some of you are voting twice. This is strange. So let's look. Let's watch this video. All right, so we're just playing this simple game. So I start with my little red circle there. I pick a vertex at random. I go halfway in between, and I don't see any discernible pattern here. So weirdly enough, I actually went from a triangle where these simple rules gave me a fractal to a square, and these simple rules just give me a cloud. Okay. Kind of uninteresting. Let's play the game one more time. So we're going to change the rules only slightly here. We're still going to do a square. We're going to pick a point, draw a line segment, pick a point in between, midway between, but this time you cannot revisit the same point. So for example, if I have a 4-sided die and I roll again, and I happen to roll a 3, well, that's not allowed because I got a 3 the first time. So I got to roll again. So, same thing. What do you think? We're going to fill the entire square with this? We're going to get a fractal? Ooh, but there's many more people going. No idea? Excellent, good, that's what I wanted. Right, so I wanted to lead you to think, maybe this is not going to do a fractal. Oh no, wait, I'm not filling in this corner, or that one, or that one, or that one. I'm actually not filling in the middle either, and if we do this, there's a square popping up over here and over here. And up top, I'm getting the same structure over and over and over again. Really simple rules are giving me something that is really robust, cool, and very pretty. So, this is what our answer should have looked like. Had we let that run for infinite time, this is what we would have gotten. So the thing on the left is called Sierpinski's Triangle, and I don't know the name of the thing on the right. But it's pretty cool looking nonetheless. All right, so fractals are kind of neat. I think we probably all have the notion of if we zoom in on these things enough, we can actually see the same pattern over and over and over again. But they also show up in nature. That's broccoli. That is fractal broccoli. When you look close enough, I have never consumed fractal broccoli. This stuff scares me. It's terrifying. Right? So if you zoom close enough, I see the entire fractal broccoli again. Now, okay, I can't zoom in forever because there are these things called atoms. Right? We've got a limit in our physical world, but this thing is fractal in nature in the sense that we could zoom in many times and see the same pattern over and over. Well, okay, so check this one out. This is river fingers coming off. This is a satellite view of a river. But check out these fingers. If you look at the finger, it kind of looks like the river itself, but then that thing also has fingers. And then the fingers have fingers. As a satellite view of this, we've actually got a fractal just sitting here in a river delta. I like this fern. This fern, so you look at this big giant fern leaf, and let's just take one chunk of that, and if you take it by itself, it actually looks like the entire fern leaf. And then if you take just this little bud on the side here, he looks like the entire fern leaf again. There are fractals everywhere. So Dr. Klein's got this problem that says, I want to protect one thing. I'm arguing that no, I want to understand nature. Fractals are all over the place. I want to understand this stuff. This is cool. Right, now blood vessels, here's another great example. I like that one. You zoom close enough, blood vessels look like more blood vessels. And my competitor here is also an astronomer at heart, so I like to pick the little astronomy ones just to pick on you and such. These are defrosting patterns on the poles of Mars. And you notice the little fractal patterns there, just like with the river deltas. This one was fantastic. So Dr. Rowley, he's a chemistry professor here on campus. He and his students were preparing this, actually just 2 days ago, that a petri dish with silver nitrate sitting in it, aqueous silver nitrate, put this filter on top of it and ran a current across it. And what it actually did is it wrote the silver onto the filter, but you notice this thing's got these nice fractal patterns. Now he was so impressed with this, he actually put it on Instagram, so I'm going to show you what he put here. I hope we can see this. This is a 2-hour experiment condensed down into 15 seconds. And it will loop over and over again. But you notice, okay, there's a little bubbling going on there, ignore that part. We've got fractals that are kind of zooming across like lightning bolts here. Because they are kind of like lightning bolts. It's electricity. Right? So, fractals are pretty. I really like them. They're really, really pretty. But are they actually useful? Like, I mean, okay, Dr. Klein's got something that is dead useful. I do not disagree with that. So, are fractals just art? No. Let's play a little game. All right? I want to ask you a question. Is that picture, with the lighting we have in this room, taken by a real person standing there with the camera on this saddle here, taking this mountain landscape, or is that computer generated? What do you think? So, real person? Computer generated? Vast majority of you, and you are correct this time, I did not lead you astray. But hold on a second. This is computer generated, and look at the detail of the mountains. The detail there, this was not some animator sitting in a dark closet at Pixar, clicking pixel by pixel. No! What he did is he gave the computer a really simple set of rules and said, do this over and over until it looks like a mountain. That's pretty cool. I mean, that's actually a pretty darn good picture. So let's try this one. Make that a little bit better. Is this real? Or is this computer generated? This is just some hardwood fort. So is this a real picture? Computer generated? Not real sure? Okay, no, of course, there's a few of those. This guy is 100% computer generated. This is not some computer animator sitting there again clicking pixel by pixel. They say, I want a tree here, here, and here. Go ahead and do this whole fractal bit and actually make it look like a tree. That is 100% computer generated. All right, what about that one? You think that's real? Yeah, you're totally right. I took that. All right, what about that one? You think that's computer generated? No. Yeah, okay, there's cool shadows in there, but this guy is totally computer generated, but look at all the detail that they get. I mean, that mountain right there, that little couloir coming up, that looks totally enticing. I want to go climb that. That looks cool. Right, but that's absolutely computer generated. This one? Absolutely computer generated. Right? Fractals are everywhere, at least in computer animation. What about that?
That's real. That's real.
Right now.
Real.
Now this was in a galaxy far, far away, a long time ago. So this is totally real. No, actually, the 1984 Return of the Jedi Death Star was one of the first fractals to actually make it into the movies. The first one, which I couldn't find a great picture for, was 1982 Star Trek Wrath of Khan. It was, anybody who's seen that movie, there's the Genesis planet at the very end. They bomb this planet with life and it just explodes with life. The whole planet was generated with fractals. That Death Star is a fractal. What movie is this? All right, so, okay, the hair that this young lady has, Wait for the next debate. There's so much math hiding right in that hair. Oh, I'm telling you. I could talk for hours about how cool that hair is mathematically. But what I want you to look at is the rock behind her. That thing looks real. Look at the trees. Those things look real. Those are fractals. This is not somebody at Pixar clicking pixel by pixel. All right, now obviously this is from the movie Up. But the formations over here, those are actually real formations in Venezuela. They're called tepuis. Now, if you kind of just ignored the fictitious balloons holding up a house, those things totally look real. And that is exactly what the tepuis look like down in Venezuela. So, Pixar wouldn't exist if it wasn't for fractals. I'm sorry, a lot of our entertainment wouldn't exist. So, let's look at how they make these things. So, very fancy, I'm going to take you to a Wikipedia page. The idea is simple. You start off with a really simple shape, you tell the computer some simple rules, and you say, go nuts, until it looks like, well, in this case, kind of something that looks like a mountain. Now, I might not have convinced you that this is useful yet, because we could probably live without some of the entertainment industry. Maybe, I don't know. So there's two famous quotes that I like. In the 1960s, there was this fundamental paper, very famous paper, called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And one of the famous quotes from that paper, I say one of because there's many, the miracle of the appropriateness of the language of mathematics for the formulation of the laws of nature is a wonderful gift which we neither understand nor deserve. Now, this gentleman was not saying, I don't understand math. He was saying, I don't understand why it's so darn useful. Why does it rear its ugly head everywhere we look? Math might initially seem like this crazy bit of abstraction, but no, it seems to be applicable everywhere. Now, another quote, apparently by Einstein, I couldn't substantiate that, so we're going to say it's by Einstein. How can it be that mathematics, being, after all, a product of human thought, which is independent of experience, is so admirably appropriate to the objects of reality? This is the story of fractals, too. Now, of course, these guys preceded fractals in their work. So to give you a glimpse of how fractals are actually used now, I did a Google Scholar search. So Google Scholar, if you don't know, is a way that you can search for peer-reviewed research articles, and you can filter these things. So I went to Google Scholar and said, I only want articles that have been published since January 1st of this year. And I had hundreds of them. I told it I wanted articles that had fractals in the title. Hundreds of them, and here's a few. This is in the last 6 weeks. Modeling groundwater flow. If you want to know where your groundwater is going, well, think about it. It's traveling through these really complex pores. That on top of those pores, there's little pits, and in those pits, there's little pits of themselves. Those pores are fractal. You want to understand groundwater? Understand fractal geometry. It's a wonderful medical paper now. These doctors were studying how cancer lesions, the little fingers that they send out into the surrounding tissue, they actually have a fractal pattern to them. And if we want to understand how to attack cancer, let's understand fractal geometry. Now, this is one of my favorite ones that I've found. Fractal art as to alleviate the symptoms of depression. Now, this was a wonderful statistics study where they were actually showing people pictures, just artwork, and seeing what happened to several different symptoms of depression. And they found that artwork that had a fractal dimension of a certain range, of fractal dimensions like a way to describe how rough the fractal is, that actually worked better to alleviate depression than most meds. And it turns out that if we go back to that fern, and we go back to all of these other fractals that I showed you in nature, they have the same fractal dimension. So the human mind's eye is so attuned to looking at nature and seeing fractals that it actually finds it quite soothing. Now, a few more. Okay, supply networks. You want your UPS truck to drive down a highway into a residential area, which kind of looks like a highway with lots more roads, then maybe into some alleyways and into, well, that's a fractal. The closer you get, you've got more and more twists and turns you can make. That's essentially a fractal. I would love to know about this one because our roads are kind of a mess. If you want to understand how asphalt actually fractures? There's a recent research paper on how that happens, and it's all fractals. Nanostructures and nanotechnology. We can't control these things with our fingers. And it turns out if we want to make them as much like nature as possible, we make them look like fractals. I'd like to understand this one. Stock market analysis. There are people using fractal geometry to understand how the stock market's actually working. And I'm sorry, Dr. Klein, there are people studying security as alternatives to RSA using fractals. Now, this is research in the last 6 weeks, right? This is not research that's ready to hit your computer tomorrow. But boy, this is the next generation of security. And now, again, my colleague here is an astronomer. I have to jab at you a little bit. This one was like hit number 3 on my Google Scholar search. There's some astronomers and some cosmologists that are saying that the structure of the dark matter in the universe is actually fractal in nature. This is modern research. And the list just goes on and on. This is the last 6 weeks' worth, and these are, what, 8 or 10 of hundreds of hits. So I think I'm going to stop there. I think fractals are everywhere. I think instead of just doing one thing and doing one thing well, they describe nature perfectly. That's it.
After that, we'll pass out some clickers and we'll give you guys a chance to vote on who you feel the winner is. So, are there any questions? Yes?
More question for Dr. Klein. Given that the premise behind the 2 large prime numbers is that it's going to take a long time to decode, whatever that time is, let's say it's a month, does Amazon have to change those things? How often do they change those 2 numbers to defeat the fact that somebody might actually be working on that for a month?
Absolutely, they do have to change those, particularly as computers get faster and faster than what was once a Herculean effort that only Amazon's proprietary computers could do. After a couple of years of Moore's Law, then all of a sudden, lots of other people could do it. So yes, I can't tell you exactly on what time scale they have to do that, but that does have to be done on a regular basis. It's an ongoing arms race. And one of the areas of research into this public key cryptography is to try to figure out methods where you have to upgrade a little bit less often, and how to do that in an effective manner as possible. So absolutely, yes, that's something that is definitely part of the process.
Or Dr. Sullivan. Could you tell us how the research into using fractals for security measures on computers looks like it's going, as in, would this be comparable to or superior to public key encryption?
I would say do a Google Scholar search, find the paper, and read it. This is high-level computer science research. I cannot claim to have understood beyond the abstract. I read the abstract and thought, yeah, that's cool. That's definitely the future of computer security.
This is a question for Dr. Sullivan. Obviously, both the cryptography and fractals are very useful for the real world. But sometimes, if you're a mathematician, you actually want to actually see how a topic touches on other parts of mathematics, and you forget about the whole real world. So, Benoit Mandelbrot was not probably thought of that highly in his lifetime by a lot of mathematicians. When Stephen Wolfram, spent 5 years coming up with his one little book, he was widely derided. Can you say what parts of mathematics are touched by fractals?
What parts of mathematics?
Yes. Yes.
Boy.
For instance, you have modular forms, elliptical. There's lots of stuff on the cryptography.
Well, I can tell you this, that Mandelbrot was not thinking about application when he came up with fractals. He was a pure mathematician who was interested in math for the sake of doing cool math. He thought it was interesting, he thought it was pretty. It has had applications, in my understanding, to the study of differential equations, which is really the study of rates at which things change. It's huge impacts on geometry. Now, geometry is not just what you learn in high school where we're drawing planes and lines and triangles. We're talking spherical geometry, hyperbolic geometry, things that really describe how space actually works. Fractal geometry has had an impact there, but this day and age, for one person to know all of mathematics, I'm not that person. I can't tell you which ones it's actually impacted.
Dr. Sullivan,
Yes.
For the last debate, you had described turbulence as something that was very difficult to characterize using math.
Yes.
Could you apply a fractal model to something that complex? Because apparently God had trouble understanding it.
You're right. You remember the quote from last time that not even God can understand turbulence. If you were here last time, that was one of the quotes. Can you apply that to understand turbulence? I'm sure people have tried. If they'd succeeded, we'd know about it, because they would probably have $1 million in their pocket.
This is a question for Dr. Klein. In the last debate, you argued for the P equals NP being the most important unsolved mathematical questions, correct? If that was proven to be correct, wouldn't that make the RSA algorithm useless in cryptography?
That would definitely have impacts, because searching for prime numbers is one of these things which is, again, so if we had a polynomial time algorithm for these exponential processes, then you can transform one to the other. So maybe that's a reason why I think probably that's not going to happen. But absolutely, this is one area where these are interrelated. We can see how these different fields of mathematics are interacting with each other.
I like how you guys are tying this into the previous debate. Keep that going. So,
Yeah, Dr. Sullivan, do you know if neurons have been attempted to be mapped by fractals?
Yeah, that's absolutely a fractal pattern. Yeah, I didn't take a picture of it. I mean, I definitely ran into them as I was surfing around looking for the pictures of this. Yeah.
Dr. Klein, so when you say that the prime numbers, like they require supercomputers and such to actually calculate, what scale is there to it? Like, is there some sort of scale towards the higher numbers you go in prime numbers, that much harder it gets?
Well, basically what I want to do, if I have a big number and I want to check whether it's prime or not, I have to divide it by all the potential divisors. I can rule out composite numbers, so I can divide it by primes, since everything can be factored into primes, and I have to check all the prime numbers up to the square root of that number. So I have to take my big number, figure out what the square root of that number is, that's okay, and then get the list of all the prime numbers between 1 and the square root of that number, and then divide my big number by that. So it's, and of course, primes are not distributed in a completely even sort of way, so there's some complexity with that. If there were, then okay, this is square root sort of time, that would be, but because there isn't, it varies. There's the whole idea behind it is that we don't have any clear pattern to where the primes are, where they occur. But that's the essential idea that has to go on.
Do you know how big the prime numbers that are being used today?
Jeepers, like the number of digits?
Yeah.
I should have looked that up before the talk. I can't tell you the exact number of digits. There are websites you can go to and you can look up what's the largest number of digits, largest known prime, publicly anyway, that you can look at and things like that. I can't tell you that just off the top of my head. Give me a second. What?
17 million digits.
Yes.
So 2
Oh.
Hold on, let's think about this. That's the number of digits. So 2 to the 57 million minus 1. Does that give you a sense of scale, Joe? Over here.
Dr. Klein, so if you're big companies such as Amazon, they have, say, the largest prime number, that's their secret number. Would that mean that they could find all the credit cards off of smaller companies that have smaller prime numbers because they know their prime roots?
Well, first of all, they're working through other things. So we've got the credit card companies that act as pipelines for all of this. But different companies can have different prime numbers, and the thing they're working on is what they're transmitting is a product of prime numbers, and so they all have different ones that they're. I guess theoretically you could end up with two of them that are exactly the same, but there's a lot of prime numbers out there. You could take a whole bunch. So the odds are going to hit the ones that their competitors are using much more.
Well, it's more like, would they be able to, I guess, hack into their competitors and find out all the credit card traffic that is going through them?
Only if their competitors were putting out the same composite number that they were. Otherwise, they're going to have just as much trouble as anybody else.
Any other questions?
I have a question, Dr. Klein, on the search for larger prime numbers. So if we could get like a good quantum computer working, would that like really up the arms there?
Okay, the idea of a quantum computer is a quantum computer rests on the idea that even one electron, a lot of the time, behaves like a wave, so it spreads out and an electron can be in many places at once. And part of the electron can do this, and part of the electron can do that, and then the pieces can come back together, and I can gain information from what the different parts of the electron do. So this could be a very efficient computer. If even one single electron can be doing many, many different things at one time, that could make for an incredibly efficient computer. If you can get that much out of one electron, and we have a lot of them, and you can just do some amazing work with that. So that would be the sort of leap forward, which might take this up into the billions or something like that.
Any other?
Dr. Sullivan, could you, fractals, explain how an epidemic, where an epidemic could go and how it would affect area?
That's a wonderful question. That's a great application. Anybody looking for a senior project in math? That is a wonderful problem. I don't know the answer to that because I'm sure someone has probably studied it, but I have not read that research. There's a lot of research on how epidemics spread through populations, how they spread along roadways, how they spread along populated areas, non-populated areas. There's tons and tons of research out there. The Centers for Disease Control understands this problem really, really, really well. Have they used fractals to do it? Sure, why not? I would say they probably have if I was to guess, but I have no idea. I've not read that research. I'm serious. Anybody who's interested for a senior project next year, talk to me. That'd be cool.
Yep.
Dr. Sullivan, I have a question for you about fractals. I'm just thinking about natural systems, and it seems to me that there must be a certain amount of information that must be understood really well about a natural system in order to model it with fractals, and then check that the result accurately models it. Is that process sort of a trial and error?
Actually, there's this really beautiful thing that I chose not to put in my talk because I didn't want to make it super math heavy, but there's this beautiful concept of fractal dimension. Now, the word dimension has a lot of connotation. We like to think of dimension as forward, back, left, right, up, down. Fractal dimension is usually a number between 1 and 2. So we can say that a picture has fractal dimension, this guy is like fractal dimension 1.35 or something like that. The word dimension has to be kind of taken with air quotes around it. What that dimension number tells you is kind of how rough the picture is, or how much the fractal in a two-dimensional space is actually filling up that 2D. So it's a measure of complexity of the fractal. Now this research paper that I talked about here, this fractal art one, what they were doing was they were using artwork that was actually known to have different fractal dimensions, everywhere from 1 up to close to 2. Good old abstract art like Jackson Pollock's that would look like you just splattered paint everywhere, turns out that has fractal dimension like 1.2. He was actually painting fractals by splattering paint all over the place. Didn't realize it, because that came right before fractals were happening. So your question is, do we have to know so much about the system to call it a fractal? Not quite. All you have to do is find a way to measure the fractal dimension of it. How rough is the thing that you're trying to measure? If you're interested, there's a great Wikipedia page on that too. You could run down that rabbit hole for hours.
All right, I think we've got time for one more question if anybody's got one.
Let's pass out some plates.
All right, let's do it.
Yeah, but I didn't take that one. I guess me and Jessica are so close to the same person in there.
We got some more.
Does everybody who wants to vote have a clicker? All right. One person, one vote. Professor Klein gave his presentation first. He will be option 1A.
We're number one. Yeah.
Professor Sullivan, that leaves you with 2B. We're not. I'm sorry. All right. Voting is open now. Please register your response. When you click, you should see a little green light. All right. Last seconds to get your votes in. Closing in 5, 4, 3, 1. Voting. And the winner is Carroll College.
No, I just changed the source. You're a CS
That winner is. one of the